is what we're dealing with today. An exponential function in general looks like this. That C that's in the front there, that's your initial value. The A that has the X as an exponent, that A.
Fourth interruption, I need the junior high cheerleaders to report to Ms. White's room at this time. Thank you.
The A there that has X as the exponent, that is your growth or decay factor. Growth or decay factor is what that's called. Okay. X is X like it's always been, and Y is Y like it's always been. So X are our values there. So we have an initial value. If we're dealing with an exponential growth type situation, like a biology type experiment type thing, when you got bacteria or something like that, that initial growth is how much bacteria was there at the beginning, our initial value. And then the growth amount is, how fast is it? It's like half-life. I don't know if y'all remember doing that in biology, half-lives and stuff like that. If you're dealing with that sort of situation, if you're talking about a financial situation, that initial amount is how much you deposited in your savings account. And then the growth rate is how much is it doubling every so many years or something like that. There's actually another formula for the finance stuff. It's a little more complicated than that for the finance. But that's the idea of the growth rate and decay rate. Hopefully your savings account's not a decay rate like mine is. But anyway. All right, here we go. We're gonna first decide is the set of ordered pairs exponential. If so, write the equation. Ooh, that sounds hard. It's not. Okay. Nothing we do in here is hard. So a set of ordered pairs, just X values and Y values. Not 30, 40, sorry. And then 4, 8. Now, a couple of different ways to do this. I'm going to show you maybe the faster way of doing this. One thing to do would be to graph all those points and see if they made an exponential type curve on the coordinate plane. An exponential curve looks something like this. That's an exponential growth curve. An exponential decay curve goes the other direction. The problem with doing it that way is we only have 5 ordered pairs. It's hard to get the idea of exactly what's going on, bless you, by looking at the graph of just 5 ordered pairs. If we had a whole data set, like we did when we were doing line of best fit and stuff, we had a whole lot more ordered pairs a lot of times when we had a real data from an experiment or something like that. Then, hey, maybe it is easier to look at a graph. But when you have just a few ordered pairs, probably not the best way of doing that. What we want to do is inspect the ordered pairs themselves. Notice the X values, nice, steady, going up by 1 every time. Okay. If it's like that, then inspecting the Y values and their relationship is a good way of going about it. Now, if this were linear, what would the Y values do? If it were linear, would they go by the same amount or different amounts? Be the same amount every time. It'd be like you're adding 5 every time. It'd be linear. If it's quadratic, then you would see a little different situation going on. But that would be even harder to see. But the linear would be pretty easy to see. With these, what you can look at is notice what's going on here. We got 5 to 10, 10 to 20, 20 to 40, 40 to 80. What's the ratio 10 divided by 5? 2. Then the next ordered pair, or y value ratio, 20 divided by 10. 2. Oh, it's the same. And then 40 divided by 20. Oh, 80 divided by 40. The ratio of the y values is the same. If the ratio of your y values, when x is going by the same amount each time, I'm about to sneeze. It won't. I'm waiting for it to come. It won't go out. Now it's gone. All right. So with a ratio of your y values, to check it that way, you have to have the x values going by the same amount each time. Okay, if they're going by different amounts, then we're going to have to go with something else, and we'll get to something else later on. Today, everything you're going to see is the x values are going by the same amount each time. So you can inspect the y values by ratio. That ratio of the y values, that is your growth factor. I say growth factor here because what kind of number is 2? Positive, bigger number, right? It's not like 1/3 or something like that. So what the 2 is doing, to get from 5 to 10, we said 5 times 2. To get from 10 to 20, we said 10 times 2. We're multiplying by 2 over and over and over. That's the exponential part. That's what an exponential does. It multiplies by the same number every time. In Algebra 2, you might have remember doing a little bit, not much, but a little bit with geometric sequences where they multiply by the same thing every time. Or you guys remember those problems when you're in elementary school and you take TCAP stuff, and they have a set of numbers. They have like 3, 6, 12, and then you had to find the next 3. So you had to recognize the pattern that was going on there, that they're doubling it every time. That was an exponential growth deal because they're multiplying by the same amount every time. Y'all remember those problems? You were doing exponentials then, you just didn't know it. Okay? So pretty much everything we do, you've been doing before, we shouldn't call it that. Okay? So that's the growth factor, which is what part of the original equation? A. The growth factor is A. So with our function, we know A is 2. I don't know why I wrote it so small, but C times 2 to the x. Now we need to know what C is. C is the initial amount. Initial amount. Well, what would, of those ordered pairs that are listed, what would be the initial amount?
It'd be 5.
Why?
Well, if you're looking at scientific data, you start with what you already have at 0, because usually the x-axis is time.
Very good. Absolutely correct. That if you think about it in terms of biological or scientific data, time of 0 is what you're starting with. Anytime whatever x is 0, that's what your initial value is going to be. Okay, so you're looking for when x is 0, it would be 5 in this case. So our equation is 5 times 2 to the x. How can you verify that? Plug in some of these other x's, right? If I plug in 1, 2 to the first is 2, 5 times 2, 10. Plug in 2, 2 squared is 4, 4 times 5, 20. It follows, it works. That's what we're getting there. Okay. So yes, it's exponential. Here's the equation that it goes with. What did I do to you on this one? All right, yeah, so I go from -1 to 1 is up by 2. 1 to 2, 2 to 3, these are by 1s. So could I inspect this set of 3 and maybe get an implied thing happening here? If it's the same for these 2 sets, then it's probably going to work after that. Not too many functions work that way. So take the second one divided by, or the next one, so it's 4 divided by 8, is what I'm trying to say. And then 2 divided by 4, which both reduce to be 1/2. Same ratio. Would this be growth or decay? Decay. Because if we're taking half of something every time, then it's getting smaller, right? And that's what decaying does, is it reduces. Okay, so if the ratio of the y values is a small fraction, like less than 1, then it's decay. If the ratio of the y values is a bigger number, bigger than 1, then it's going to be growth. That's the difference in the two. Okay? Growth, bigger number, larger than 1. Decay, less than 1. Okay? Small fraction. Okay, now that gives us that it's exponential because we got the same ratio on our y values. Now, what about the function, the actual equation for that? We know a is 1/2, but we don't have the ordered pair for 0. How could I find that? Would it be 32 times 1/2? Because what's 32? Okay. What if I didn't? What if I just use my equation that I've got set up started to find C? Don't I have a bunch of x and y values? Can I just plug one of those in? We'll plug the easy one in. 1. Right, 1/8. 1/2 to the first power's 1/2, right? So we have 1/2 times C equals 8. And then how do we get C by itself? Divide by half or multiply by 2 is the same thing, right? So it is 16. C is 16. But I'm using just an ordered pair to get there. So that if we don't have something nice going on there, and we happen to know the growth or decay rate, we can build that function by using one of our ordered pairs. What you guys were doing was perfectly fine, and it works great, especially for this particular problem. But I'm trying to give you maybe something that's a little more universal tool. Solve it with the equation that you know it's supposed to look like. Use one ordered pair that you have. Okay. So we know C is 16, so the final function out of that thing would be f of x is 16 times 1/2 to the x. And I usually, if it's a fraction, I usually just put it in parentheses. That's a fairly common thing to see, is just that way you know it's 1/2 to the x power, not just the 1 part. So anyway, there's our function for that. So being able to compare the y values, the ratio of the y values, in order to determine if a set of ordered pairs is exponential. All right. Now let's crawl back to chapter 3 stuff. You guys remember doing the transformation things, like it shifts up 4 units, left 5, and all those things that were involved in the equation to do that? We're going to do the same thing, but with exponentials. Okay, so let's describe the transformation of y equals 2 to the x. Okay, that's our parent graph. That's the original. Okay, and we're going to describe what's happening to it based on the information. 2 to the x, and then a plus 4 on the outside there. What does that do to it? Shift it up, right, up, down, left, right. Up 4. Why up 4? It's on the outside, so it's a vertical thing, and it goes, and it's positive, so we're going to go up 4. Could you graph those with the graphing calculator and see that happening? Yeah. You go to your graphing calculator, clear out some junk that we were doing the other day. If you 2 to the x, 2, caret symbol, x, this is what the original looks like. Here, that growth, the growth curve. And if I graphed that second equation, 2 raised to the x, and then plus 4 on the outside, here's the one raised up. Notice that the blue one is the original and goes through 1 on the y-axis. This one goes through 2, 3, 4, 5 on the y-axis. Well, that's up 4 units out of that. Okay. So, nice graph can help you there. But the idea of this is that you don't have to graph it, that you just know. So it saves you time and effort involved in that. Let's do this. F of x. Still on the 2 to the x. It doesn't matter what the base is here. If you did a 4 to the x or anything, it doesn't matter. The shift is all the same. All those things. We're just using 2 to the x as an example. 2 to the x minus 3. What's that one going to do? Good job. Right through. Because it's happening to the x, and remember, anything happens to the x, it's the opposite. So a minus 3 moves to the right 3. A plus 3 would move to the left 3. Okay. One more of those. Let's do a tough one. 2 to the negative x, and then a minus 5 on the outside. 2 to the negative x minus 5. I agree with the down 5. Mike said down 5. I agree with that part. What does that negative on the x do? Across what? The y-axis. Because we're changing the sign of the x's. So if x was positive 2, if I change the sign of it, throws it over here to negative 2. Okay, so reflect across y-axis. If the negative were down here in front, like in front of the negative 2, that would be a reflection across the x-axis. If it's with the x, it's going to be a reflection across the y-axis because it's going left to right. There. The negative in front would be up and down because it's on the outside. Basically, is the way you want to think about that. So this one goes down 5 and it's reflected across the y-axis. Just go back and refresh yourself on those things. You're going to ask general questions about those. And keep in mind, you can graph the original and then graph the one they're asking about and kind of get a better vision of what's happening if you're having trouble visualizing it. I know spatial sense can sometimes be an issue with this stuff. All right, let's get to what I think is the fun part of this lesson. Solve exponential equations. I always feel better when I'm solving an equation because I get an answer and I've done something. These general theory type ideas are great and good for understanding and wonderful, but I sure like getting x equals 5 or x equals something to say that's right, and I know if it's an equation I can go back and check, make sure I did it right. So solving equations that's what I like about math, is equations work. Okay, now exponential equations means that we've got a variable in the exponent. which is different than we've had before. But the good news is everyone should have done this in Algebra 2. If you didn't, it's not hard. If you don't remember it, it's not hard. Here's the key. If it's an exponential equation, we want the bases on each side to be the same. Look at this problem. We got 2 to the x plus 5 equals 2 to the 8. What part's the base? The 2's. If the bases are the same, then what do we know about those exponents? Yeah, those exponents have to be equal to each other. So if we can get the bases to be the same, then all we got to do is do the equation for the exponents. X plus 5 equals 8, and solve it. X plus 5 equals 8. That's a pretty easy equation to solve, right? X equals 3. I can check that. 3 plus 5 is 8. 2 to the 8th better equal 2 to the 8th. Forever and always. If it doesn't, then we probably don't have much time left. Okay? Because we're going to hurtle through space toward the sun and burn up. Now here's where it's a little more difficult. You know that's not going to be easy like that. You know I know. Here we have 2 to the x plus 1 is equal to 16. 16 is what? 2 to the 4th power. We can change 16 into 2 to a power. Ha! 2 to the x plus 1 equals 2 to the 4th power. And then, oh, now the bases are the same. I've got another easy equation to solve. X plus 1 equals 4. I solve that. X equals 3 again. I was doing some of these same examples Monday night with my night class at Parsons, and like the first 3 that I made up had the same answer. And one got in the back. Is 3 always the answer? Maybe dead seriously. So I was like, for you, yes. You have a good shot. 3 out of all the numbers in the world. Pretty good idea. Let's do something with a 3 here. 3 to the 5x. Ooh, weird. Is equal to 81. That's a good number. Okay. How so? Okay. What if we don't know much about 81? I happen to know, I haven't memorized that 81 is 3 to the 4th power. Not a ton of people have that memorized. Y'all remember doing factor trees when you were from a while back? Break down the 81. I know 81 is 9 times 9. Most of us should know that. And then 9 times 9 is 3 and 3. Or 9's both turn into 3 times 3. So 81 is actually 3 4 times. 3 to the 4th power. Now we have the bases the same. And we set up our equation then. 5x is equal to 4. Divided by 5. 4/5. And the guy in the back said, oh man, it's not 3. He thought he had it made. All right, so here we've had a couple where we've had to change one side into something. It doesn't stay that easy. Okay. 4 to the 2x minus 1. So we're hoping for something over on the other side that's like 4 squared or 16 or maybe it's 64 or 64 times 4, 256. Something. We're hoping it's that. Jerk. Put an 8 there. So here we have to think a little bit more. Because 8 is 4 times 2, not 4 squared. Yeah, we can break both of them down to 2's, right? Because we know that 4 is 2 squared and 8 is 2 to the third power. So this is 2 squared to the 2x minus 1. And this is 2 to the third. What's the rule for exponents here? The 2 on this 2 and the 2. Say it again. Multiply. Yeah, that's right. We're going to multiply 2 times 2x minus 1. So that's going to give us 4x minus 2 is equal to 3. Right? What can we do with that? Add 2 to both sides. 4x equals 5. And divide by 4. Yeah, last step. X equals 5 over 4. That's neat. Do another. What if we had 27 equals 9 to the 2x? Turn it around the other way. All right. 27, 3 to the third power. 9 is 3 squared. What do we do with those exponents? Multiply them. So that's 4x is equal to 3. Divided by 4. 3/4 is x. Let's change it up a little bit then. Let's say we had 9 to the 5x equals 1 over 27. Looks like a very similar problem. But yeah. Ooh, somebody remembers exponent rules. That this is like 27, which is 3 to the third, but it's on the bottom, so you use a negative exponent. So that is 3 to the negative 3. And then 9 is still 3 squared. Not 2 squared, but 3 squared. And then you multiply your exponents, so that's 10x equals negative 3. Negative 3/10. So if you've got a fraction, you want to think, oh, I've probably got a negative exponent in there. So think about, okay, especially if it's 1 over a number. Think, oh, that's 27 is what? And then make it a negative exponent. Really an easy thing to do there. Okay. Go to a more interesting problem. 4 to the 3x squared equals 8 to the x. So it's kind of similar to one we've done before, but a major difference in the way the exponents are. Indeed. So what's our exponential we're looking for here? 2 to a power, right? So 4 is 2 squared to the 3x squared. And 8 is 2 cubed to the x. So we have 6x squared equals 3x. And we've got to remember, how do we solve that type of equation? It's got an x squared. What do we have to do first? Get it equal to 0. Very good. Anytime we got an exponent on our variable, Then we've got to get it equal to 0. So subtract 3x. 6x squared minus 3x equals 0. And then we've got options, right? Because it's quadratic. We could factor it. How would we factor that? Pull a what out? 3x, because they both have x's, so that'd be 2x minus 1. So factoring with the GCF there. And then what do we do with each of those again? Yeah, 3x equals 0. And then 2x minus 1 equals 0. Solve each of those. X equals 0. Add 1, 2x equals 1. And then divide by 2. X is 1/2. We get two answers for that. We had a quadratic to begin with, so should get two answers for that. If I plugged a 0 in the original problem, 4 to the 0 power, 1. 8 to the 0 power is 1. I plug in 1/2 in there. 4 to the 3/4 power is equal to 8 to the 1/2 power. That does work as well. So both of those check in the original problem. So solving a quadratic, something you're supposed to know how to do, right? We had a couple of sections in our chapter 4 about solving quadratics. All right, here's a funky one. Using E as a base, it's not. It's a little lagging behind here. Give it a second. There it goes. All right. E to the 2x and e to the x minus 1. That's not just a variable e. E is the exponential number. E to the first power is like 2.71 and a whole bunch of decimals after that. It's kind of like pi. It's one of those numbers that came up enough. They gave it its own name out of that. So that's that E. On your graphing calculator, there's a button for each one. Yeah, so the bases are the same, so it really doesn't matter what it is, right? Yeah. So the bases are the same, so we set that up, 2x equals x minus 1. And then here's another one where x is on both sides, right? Yeah, do I have to get this one equal to 0? No, because why? There's not an x squared. So all we got to do is just get x by itself. So, and it ends up being x is negative 1. Right? Eventually. Sorry.
You said something about how when we're doing the equation, we got 127. What if it was something like 3
If it were 2 over 27, then that'll be in the next section. How to do that. If it's 3 over 27, you would reduce that to 1/9 and then do your exponential stuff. If it's a weird fraction like 2 over 27 that won't reduce and you can't rewrite it exponentially, then we're going to use logarithms to solve it, which would be next step. Okay. All right. So we got x equals negative 1. That's easy. Let's do one more here. Of course. The last example. All right. I'll do it on the board. Because you need to see one like this for sure. Okay. Example M. E to the 7, I'm writing U. E to the 7x, I'm trying to remember what it is. Times e to the x squared. Okay. Is equal to e to the negative 12. Why do you do that? That's right. Because what's the same? The bases are the same. So yes, the exponent rule here is if you're multiplying two things together that have the same base, Christian said you add those together. So this is really e to the x squared plus 7x equals e to the negative 12. Right? And then the bases are the same, so our equation just is this stuff. So we got x squared plus 7x equals negative 12. That's our equation that we're going to work. Got to be equal to 0. So x squared plus 7x plus 12. No, that's a quadratic equation. How do I do it? The factor by x method or quadratic formula. Either of those will get you both answers. Doesn't matter which one. So if I factor it with the x, a little sticky thing. Alright, so factor it with the x, you got to multiply to be 12, add to be 7, that's 4 and 3. So our factors are x plus 4, x plus 3. So what are our answers? Negative 4 and negative 3. Not too difficult, right? So the new part, pretty easy, right? The old part, still pretty easy. Nothing really, just rocket science here on this stuff. So here's the page 431, 3 through 59, and 61 through 84, and then 101 through 107. Kind of broken sets there, problems to look at. Not bad. And I'll go ahead and I'm going to work this on here. E to the x squared plus 7x is e to the negative 12. This is our equation now. And then, so x squared plus 7x plus 12 equals 0. X method, 4 and 3. So x equals negative 4 and negative 3. Page 431, 3 through 59, 61 through 84. Yeah. 101 through 107.